today we will finally deal with Czech cohomology. So okay, we know what a cohomological complex is, and we know how to take the cohomology of such complex. Czech cohomology is cohomology, so we need to build a cohomological complex, which refers to sheaves. So we take a sheaf of abelian groups on a paracompact Hausdorff. Hausdorff is T2, separation of points by the open sets, topological space. So we don't need to do it for manifolds, we can just do it for any good enough topological space. And then we take locally finite open cover by open sets. Okay. And now we take C0 U of F. So this is a thing which depends, of course, on the sheaf U and on the cover, on the sheaf F and on the cover U. So we define this to be the product, so not the sum, but the product of the spaces of sections of the sheaf. Okay, so you simply take over each of these open sets, you take a section. And for C1, it's the same, but instead of taking U alpha, you take intersections between U alpha 0 and U alpha 1. So we take it on the smaller sets. And notice that we do not require alpha 0 and alpha 1 to be distinct. So for instance, this also includes this one somehow. And in general, for index P, we take the intersection of P plus 1 objects. So from alpha 0 to alpha P, F U0 alpha, sorry, U of alpha 0 intersected alpha P. And I will try to keep writing this intersection as they are, but sometimes when I'm running out of space, so I'll say notation, sometimes I will write instead of alpha 0 intersected U alpha P, we'll just write U and then alpha 0 alpha P to mean the intersection. Yeah? So what is an element here? So as we say, an element of CPUF is a family F alpha 0 alpha P of sections on, sorry, not of, but of F on sections on U alpha intersected alpha P. And as I said before, yeah, but an index can appear more than one. More than once. And an element of CP UF is called a P cochain of F. And okay, so the idea here is that we have this objects which increase in index, and we want to define the operator that traces the index, so some kind of differential, if we take the parallel with the RAM cohomology. So we define the co-boundary operator. Delta p plus 1, and of course we will often drop this p plus 1 index here. That goes from Cp to Cp plus 1. And it takes, grab some more space. It takes a P cochain and it sends it to the P plus 1 cochain given by this alternating product during sum. So J goes from 0 to P plus 1, and it's -1 to the J, F a 0, then we skip a J, usual notation that we use for the projective space, P plus 1, restricted to U alpha 0 intersected U alpha P plus 1. Okay. And of course, this notation here, this restriction notation, is what we introduce in general for sheaves. This actually means the restriction map for sheaves. Yeah. So we're used to this now because we always think of these f's are functions. They're usually sections of some bundle. But in principle, instead of writing the restriction like this, what I should really do, we use the map R UV, yeah, where U is the intersection of P plus 1 of them, and V is the intersection of P plus 2. So maybe let's just look at this for P equals 0. To have a better idea of what's going on. So we have an element of C0, and we want to apply the co-boundary operator to it. So what I want to look at is the alpha beta term of this. Okay. So we look here, and for J equals 0, we need to skip the first index. So we skip alpha, and we put F beta, and we restrict it. And then for J equal 1, we get a minus sign, and then we have to skip the second index. So we get F alpha, and again, restrict it to U alpha intersected U beta. Okay, so this is what it is. Let's also look at it for P equal 1. So this is just to familiarize, especially because then we will have a theorem. We really use this delta 1 and delta 2 in particular. So I just want to have an explicit expression for them. So again, F alpha beta, and here we have alpha, beta, gamma. And okay, first we have to eliminate alpha. So you get F, beta, gamma. And okay, I should restrict them, but I will skip that and just restrict at the end. This is not legal technically, right? But we understand what we mean. Then you skip beta, and you get alpha gamma with a minus sign. And then you skip gamma, and you have alpha beta. And you restrict to U alpha beta gamma, which is intersection U alpha intersected U beta intersected U gamma. So again, just saying that this is a bit of abusive notation because this object lives on U beta intersected U gamma. This one lives on U alpha intersected U gamma. This one lives on U alpha intersected U beta. So you can't really just sum them up as they are. You should first restrict them and then sum them up. Especially because these are just elements of a sheaf. They're not just functions where you're like, oh, where this makes sense. You know, these are really just elements of the sheaf. So the restriction is just some abstract thing. But we know what we mean when we read this. Okay. And of course, now the lemma is that this is a cohomological complex. So if you compose two of this, you get identically 0. And the proof is an exercise. A computing exercise, so nothing fancy. And of course, every time we have a cohomological complex, we like to give names to the elements of the kernels and elements of the image. So the elements of the kernels are p cocycles. So these are the ones that represent elements in the cohomology, while the image of this are p coboundaries. Okay, so just an element is a p cochain. If you're in the kernel, you're p cocycle. If you're in the image, you're a p coboundary. So exact ones are p coboundaries and closed ones are p cocycles. And so the cohomology of this complex, so the cohomology of the cohomological complex C dot UF comma delta dot is denoted by H dot with the thingy here to remember check UF, and it is called the Czech cohomology. The Czech cohomology of F with respect to U. Just a quick observation about the zeroth cohomology. So this is just the kernel, yeah, of the first operator. Well, this is just the global sections. Why? Because if the delta operator of F alpha is 0, then what this means is that F beta minus F alpha on, again, this is fake restriction. This is 0. Yeah, so since F is a sheaf, there actually exists an F such that F restricted to U alpha is precisely F alpha. Yeah, they glue together. Okay. So elements of this first cohomology group, of this, sorry, zeroth cohomology group, are nothing but the global sections of your sheaf. And okay, but you see this, what we created now is not, so, I mean, this is already interesting because this does not depend on the covering, right? This depends only on the sheaf. So the zeroth cohomology depends only on the sheaf, not on the cover, even if in principle, of course, by how we define the cohomology complex, this heavily depends on the cover. So let's just explore a bit how this cohomology changes when we change a cover. So let's say that we have U prime. Okay, this is in some index. And let's say this is a refining of our original cover. And we write that U prime is this symbol here. Okay. So the refining is bigger. So this symbol is like the greater or equal, but with curvy lines. And Then we take a map phi from the set of indexes to the set of indexes. Oh. So the map from here to here. And it just basically is something to tell you. So this is a refining. So each u beta prime is contained in one of these u alphas. So this phi just gives you one of them. Okay, just one of them. And then we have a map, which we call Rho P phi, that goes from the pico chains with respect to u to the pico chains with respect to u prime. And of course, this map is just the restriction. Yeah. So you take Rho phi p of a pico chain, so f alpha 0 alpha p. And what is this at index beta 0 beta p? Well, we simply replace all these indexes with the corresponding one. So phi beta 0, phi beta p. And of course, then we have to restrict it to the correct set. So this would be u prime beta 0 beta p. Okay. Sorry, maybe I shouldn't put the parentheses here because I'm looking at the precise one. So such that. Okay. So here I think the idea is clear. You want to know what is happening. So we have to give you a pico chain, and I tell you that on the point beta 0 beta p, for each of these betas, I choose one of the alphas. So this is my map phi. Okay. And I simply look at that. I look at what the pico chain is there, and then I restrict it. Okay. So not only this is well defined, but it satisfies the delta composed rho phi is rho phi composed delta. And of course, this is delta p plus 1. I mean, I should put the p's and the p plus 1s. But again, this is something we skip every time we have a chance. Okay, because simply these are, I mean, when you apply delta, this is just like a linear combination. And this is just like replacing indexes. So the point is that the indexes are replaced with the same phi. So if you have a beta 0, you don't every time pick a different alpha, but you always choose the same. So that's why you have commuting. And so what this means is that this is a morphism of cohomological complexes. Cohomological complexes. So not only, so what are the two cohomological complexes? One is the one with u, and one is the one with u prime. Okay. And every time we have a morphism of cohomological complexes, it induces a map in cohomology, which we call Rho, which of course still depends on phi. And just give you a quick fact is that this induced morphism Rho, I mean, I'm using the same letter, but I mean this one. So the one in cohomology is actually independent of phi. It looks very dependent, of course, and at the level of cochains, it is dependent. But once you go into cohomology, so you only look at it for picocycles and you quotient out co-boundaries, then this becomes independent of phi. It doesn't matter what you chose. We will not prove this. We'll just take it as a fact. Okay, so now not only we have a lot of different cohomological complexes, right? One for each cover, but we also have a directed system of them, right? Because every time I have cover, I can always take a refinement. And if I have two cover, I can take a common refinement. So this is a directed system, which means I can take the direct limit. So the Czech cohomology of f over x, so now is without respect to a cover, is the direct limit h p x f, which is just the direct limit of h hat p u f for non-negative p's. Okay. And this is, of course, the limit is indexed over the directed set of coverings with order given by this wiggly less or equal. Okay. And one thing that we know, thanks to direct limits, so for every, so let's say observation, for every cover u, so not every cover, but every, what is it, the locally finite open cover, yeah, these are what we mean by cover now. There exists a morphism into the cohomology, which will phi u h hat p u f h p x f. So not only this, but every element here of the direct limit can be represented in one of these groups. Yeah, this is the property of the direct limit. So every element here admits a u and an element in h hat p of uf, which maps to the element. So everything is represented in one of this. Okay. Okay, so this all looks, I would say, very abstract and bit maybe nonsensical at the moment, but we will immediately see a theorem which kind of gives a reason why we would ever consider something like this. So theorem, if we take a complex manifold, then the H1M of so the first Czech cohomology group with values in the sheaf of never zero holomorphic functions is isomorphic to the Picard group of M. So the Picard group being the group of all line bundles. Okay, so this cohomologies do encode something. That's what I'm trying to say here. The proof is not hard, but you do have to be careful about, this. I mean, just the way we define this. Basically, you just have to write down very explicitly what is the definition of this object. Okay, so let's do that. So we take sigma, which is an element here. So this is the direct limit. Yeah, so in particular, there exists a cover alpha of M and a co-chain that represents the sigma. So these are G alpha betas in O star M U alpha intersected U beta, such that sigma is represented by this G alpha beta. And of course, this is a cocycle. So delta of this G alpha beta must be 0. Okay. This G alpha beta is not unique, of course, because you have to quotient out the P co-boundaries. But we'll deal with that later. So just one thing you have to be careful here is that when we wrote, where was it? These inequalities, sorry, not equalities, this formulas here. So just to check, what is the meaning of delta at the level 0 and delta at the level 1, blah, blah, blah. We are using additive notation because we said that F is a sheaf of abelian groups, and usually when you have abelian groups, you use additive notation. Now, O star, where is it? O star M is a sheaf of abelian groups, but under multiplicative notation. Okay. So what this means is not that G alpha beta plus minus G beta gamma plus G beta alpha is 0, but it means that G alpha beta times G beta gamma times G gamma alpha is the identity. What identity? It's 1. Okay. So this is the equivalent to this thing is 0. And instead of putting a minus here, basically what we would have is 1 divided G of alpha gamma, right? But this is the same as G gamma alpha. So we just had to swap one of them, the 2 coordinates. And why is that true? Well, because if you take, I think, alpha gamma, then what you get is that G alpha gamma is the same as G gamma alpha inverse. So let's say basically what I'm trying to say here is that this G alpha beta satisfies cocycle conditions, because this is precisely the cocycle condition that we saw back when we were doing line bundles. Satisfies cocycle conditions. So in particular, it defines a line bundle. Which we call L. So of course the idea now is to map this element sigma to that bundle L. But before we do that, we have to check that this is well defined. So we have to say, okay, let's say that we have another representative. So if G alpha beta prime is another representative of sigma. Well, first of all, we can assume that they're defined on the same cover. They meaning G alpha beta and G alpha beta prime. Okay, and this of course we can do again by the property of the direct limit. Now, if you take a refinement here and you take the image of G alpha beta in that refinement, that still is a representative of sigma. So you just take a common refinement and you take the representative there. And of course, they're mapped to the same line bundle L. Okay, so what does it mean that they represent the same sigma? They represent the same sigma. So what it means is that if you take one, multiply the inverse of the other, this is the neutral element in this group. But what does it mean to be the neutral element in this group? It means you are in the image of delta 1. So there exists a zero cochain, value is master m, such that the image of this cochain is g alpha beta times g alpha beta prime inverse. Okay, we don't really have yet an explicit expression for what this means. But let's just see it. So this one, again, we're in multiplicative notation, not in additive notation. So this is not f beta minus f alpha, but it's f beta divided f alpha. And we can do this because these are non-zero holomorphic functions. Well, this is equal to g alpha beta divided g prime alpha beta. Okay. And in particular, so if you remember, so g alpha beta defines a line bundle, g alpha beta prime defines a line bundle. And whenever, so this was back, I think at least a month and a half ago, whenever you have a function, a set of functions f alphas which satisfy this, it determines an isomorphism of line bundles. So maybe, I mean, we saw this, so maybe now it's something you don't remember, but we saw this. And so in particular, two line bundles are isomorphic, therefore they're the same element in the Picard group. So this map is well defined. Okay, so let's just recap what the map does. You take an element here. Since this is a direct limit, it has a, let's call it a local representative. And this local representative is a 2 cochain, therefore it satisfies cocycle condition. So every time you have functions which satisfy the cocycle condition, this gives you a bundle. And we take that bundle as our image in the Picard group. Okay, so this is one direction. What about the opposite? Let's say that we have a bundle. What is the corresponding element in the Picard group? So vice versa, a line bundle L with transition functions g alpha beta. So these transition functions leave on some cover, but we know that every time, so we have this map, right? Every time you have an element here, you can always just map it to the cohomology. So this defines an element sigma in here. Okay. And the reason this is a picocycle, yeah. So why is the delta of gamma alpha beta 0? Well, because gamma alpha beta is our transition function, so they satisfy cocycle conditions. Yeah. So they're in the kernel, so they do have a representative in here. And what happens if you have a line bundle which is isomorphic to it? We also have to check that this is well defined, yeah. Then the transition functions, transition functions for this new bundle give the same element. Same element sigma. Why is this? Well, simply for what we did before, we know that because this is an if and only if, yeah. This arrow here, it's not just one direction; it's both direction. So I'll put the orange dot here to remember this is this implication. So if we have two isomorphic line bundles with G alpha beta and G alpha prime, then there exists this F alpha beta, which satisfy this, but this is precisely the same condition as being the image of a zero cocycle, zero cochain. In particular, you're the same element. Okay, and even if you change cover, again, we have all these maps that go from a bigger cover to a smaller cover, or a common refinement if you take two of them. So everything works. Okay, the only thing we're left, so we have this map, which is well defined. It has an inverse, so we have a bijection. The only thing we have to check still is that this is a morphism, because I'm not just saying that this is, you know, a bijection. I'm really saying that this is an isomorphism of abelian groups. So what are the transition functions? Since the transition functions of a product are the product of the transition function. This bijection is an isomorphism. So bijection is an isomorphism. Because what is the group structure? Yeah, maybe one thing we didn't look at when we define this object here. This is an infinite product, so the group structure it's simply the group structure that you get from a product. Okay, so it's component-wise. Okay, and in our case, since we have group under multiplication, what it means to take the product of two cocycle G alpha beta and G alpha beta prime, well, you just take the cocycle G alpha beta times G alpha beta prime. This is your product. Okay. So this concludes the proof. So maybe just to repeat the key point here, which maybe is the one which is a bit hard to remember from since we did it some time ago, I say is this one. Yeah, this equality here. That two line bundles are isomorphic if and only if there exists a collection of never zero functions f alpha which satisfy this equality. Okay. Yeah, because this is just by you just translate this in terms of cohomology, of Czech cohomology, and this precisely means what we want it to mean, let's say. Any questions?
No, I think
Okay.
not this far.
Okay. So now we defined what is this Czech cohomology, and we already saw, I mean, this was just a small theorem to tell you what is the importance of this, what would you ever consider something like this, and the point that this is very much linked to other properties of the manifolds and to other objects we already seen. Now, of course, when we have new objects, we also want to have morphisms between this object and see how morphisms behave. So we take two sheaves of abelian groups. Over X. And we take phi from F to G morphism. So this is a morphism of sheaves. And the cover. So again, open locally finite. Well, since this is a morphism of sheaves, what it means is that if you take the restriction in G, this commutes with phi. I mean, restrictions commute with phi. And therefore, the induced map of cochains which simply takes a cochain and maps it component-wise. Is well defined. And satisfies phi tilde compose delta is delta compose phi tilde. Okay, simply because this is a morphism of sheaves. So every time, so if you have this morphism of sheaves, it induces a morphism of cohomological complexes. And of course, every time we have a morphism of cohomological complexes, this induces a mapping cohomology. Yeah, so we take the corresponding cohomology of the complexes and we have an induced map. So what we will love now is that this map descends also to the direct limit. So to the Czech cohomology without respect to a cover. And so let's see what happens if we take a refinement. So let's say we take a refinement. And then we have the map Rho, which we saw before, which is just a restriction, yeah? And we said that we didn't prove, but we did say that this is independent of the map phi that you chose before. Not this phi, but the one from before. So let's say this is the induced morphism. Then we do have the draw composed phi u is the same as phi u prime composed. Okay. So first restricting and then going to G is the same as going to G and then restricting. Also in cohomology. So everything descends to the direct limit. And we have an induced map, which we still call phi p. From the Czech cohomology to the Czech cohomology. Okay. So this is nice. Basically, we started with sheaf morphism, and what we get is a morphism in Czech cohomology. And maybe let's just look at a few obvious properties. So for p equals 0, this is just the map phi x from fx to gx. Because we said that for p equals 0, this is just all global sections of f, and this is just all global section of g. And if you follow the induced maps, this is simply just phi. When as an open set, you take the all of x. So that's another thing. Another obvious thing is that if you start with the identity map, so if f is equal g, and this is the identity map, then the induced map is also the identity map. Okay. And then also we have composition. So if psi is a morphism from G to H, and H is another sheaf of abelian groups, then the map induced by the composition is the composition of the induced maps. Okay, this is just some observations which, okay, maybe one needs to think about, oh, why is this true? And you should really follow all of this, but they're not hard, so we will not focus on them. Okay, so now it's time for the big theorem of today. And this is really a big theorem. And I'd say it's very nice and tricky. So we start again with a Hausdorff and para compact topological space. And we take 0, E, F, G, 0, short, exact sequence of abelian groups. And then there exists a long exact sequence HPXE, HPXF, HPXG, HP plus 1 XE, etc., etc. You're like, oh, but we know this.
Yeah, just are these sheaves of abelian groups or
Yes.
EFG?
Yeah,
Okay,
sequence
just
of sheaves of abelian groups. Yes.
sorry. Okay.
Sheaves of abelian groups. Thank
Then
you. Yeah, otherwise doesn't make much sense. Okay, then you look at this and you're like, oh, but we saw this. I don't need to prove this. We know that this is true. You have a short exact sequence. This produces a long exact sequence in cohomology. The problem is that, so you're like, so careful before we go with the proof, careful. To have a long exact sequence in cohomology, you need a short, so to have a long exact sequence in cohomology using the snake lemma. That is what we used. Using the snake's lemma, you need a short exact sequence of cohomological complexes. Right? You start with a short exact sequence of cohomological complexes, you apply the snake lemma, and you get this long exact sequence. Problem? This is not the cohomological complex sequence. What is the cohomological complex sequence? Is this one. Right? These groups here are, well, they're not even the cohomology of this. They're like the direct limit of this cohomology. But of course, if it's true for every u, then it is true also for the direct limit. So the problem is that if you take this is exact, but this is the last part, you don't have it. So why? Well, just try to remember, just look at it here. Remember that if we take a set U and we take sections over a set U, you get 0, E of U, F of U, G of U, but this last map might not be surjective. And this is the old reason why we define the image as we defined it and blah, blah, blah. So this is the same thing because it's just as the product of similar things. So this is not a long exact sequence, a short exact sequence of cohomological complexes. So you cannot just apply the snake lemma and then take the direct limit and say you're done. Does not work. Okay, so the proof needs to be a bit more involved, but it still works. That's the beauty of it. And the point is that it works. It doesn't work at the level of u. So if instead of x here, I put u, and I take the Czech homology with respect to u, this will not work because this is not an exact sequence. But once I take the direct limit, it does work. And the intuitive reason behind this is that when you take the direct limit, it just means that you have to find one cover for which this works. And you don't even need to find like one cover for which it works overall, but it's like for every element here, sorry, not here, for every element not here, but like, yeah, let's say for every element here, you need to find one cover u prime for which, let's say, this is correct. And like you don't even need to find one cover which works for everything. You just need for every element it's its own cover, because you take intent the direct limit and everything works. Okay, so this is the power also of the direct limit. So this was the intuitive reasoning behind it. Let's now dwell with the complete proof. So we want to show, so let's just repeat this last thing. We want to show that given an element in HPXG, there exists U cover and an element G alpha 0 alpha P, which is a cochain, on this set U, which represents the sigma. So remember, this is the map from HP U of G into HPXG. And this G is in the image. So there exists an F alpha 0 alpha P, which is a cochain of F. Such that F alpha 0 alpha P is mapped indeed to this G alpha 0 alpha P. Okay, and for what I was saying before, if this is true, we're done. Why are we done? Well, because then we can just, for that specific cover U, we can just reason as in the snake lemma, and you're done. Okay. So let's say, I mean, the point is that we need to define the map that comes from the snake lemma. So we have to define where the sigma goes to. So we are here, we have a sigma here. Where does it go? Where does it go here? And the idea is that you want to follow the steps of the snake lemma, but what you're missing is that this map is surjective. So you don't know that he has a pre-image here. Okay. But if I find one specific cover which does have a pre-image, then I go back all the way, and I do find an element in here, like a P plus 1 cochain of E. And the fact is that when then you go down to the direct limit, that's going to be your image of sigma. Okay, so how do we obtain? We need to obtain both the cover and the element. To obtain U and G alpha 0 alpha P, start with locally finite open cover U prime. U alpha prime, and again we take alpha in some index U prime, and a cocycle which represents sigma. Yeah, this pair certainly exists, representing sigma. Because sigma is an element of the cohomology, so particularly it's an element of the direct limit, so there is a representative. And we need to somewhat modify this representative so that it is in the image of yeah, so that there exists this F. Okay, so since X is paracompact, so by paracompactness, for every point in the manifold, or well, in the topological space, there exists an open neighborhood of X such that ux is contained in u alpha prime for finitely many alphas. Okay, this is just paracompactness. And so x is gonna be in here for only finitely many, because the cover is a locally finite cover. We can shrink ux and assume that if x is in u alpha prime, then ux is contained in u alpha prime. Okay. So, I mean, simply you can say that, okay, this x is only infinitely many of these open sets. I take a neighborhood of this point, this ux, and then I simply intersect it with all these u alpha primes. Right? And I take that as my neighborhood of x. And furthermore, we can assume that g alpha 0 alpha be restricted to ux as a preimage in fux. Why is that? Because we started with a short exact sequence of sheaves. Okay, so for small enough u, we do have exactness. Okay, because we do have exactness at the level of stalks, basically. So there is one neighborhood where it works, and we just keep shrinking so that everything is fine. So we do have a preimage, and we do have that this neighborhood is containing only finitely many of this. And of course, I mean, we need to ask that this set is not empty. So this is whenever this is not empty. Okay, now we proceed a bit as we did already. So we choose with double O a phi from x to I, such that x is contained in u prime of this image, u prime, for every x in x. Okay. But then u which is simply the union of all these neighborhoods, yeah, is a refinement of u prime. And why is it a refinement? Because each one of this is contained in a previous one. And since it's a refinement, we can look at the image of g alpha 0, g alpha p in it. Is precisely what we're looking for. We were looking for. Why is this? Well, because we know that once we restrict to this u alpha prime, to this ux, then this element here, so the image of g alpha beta in cpug, so this thing, as a preimage. Okay, and so that's exactly what we were looking for. So this, now we have this cover U and we have this element G alpha beta, and which has a preimage in F, and therefore we're done. Okay, so again, just to repeat the idea one more time, we would like to use the snake lemma. We cannot, because this is not an exact sequence of cohomological complexes. But the trick here is that you don't need this sequence to be exact, but you're allowed to take a refinement of U. And the point is that you don't need like a refinement of U for which the sequence is an exact sequence of cohomological complexes, but like for every element, you need a preimage, and that's it. In a suitable refinement. Okay, and this is all thanks to the property of the direct limit. And how do you obtain it? Because, okay, so this was the initial part. We're saying, okay, we only need that in a suitable refinement, we have a preimage. But how do you get a preimage in a suitable refinement? Well, basically you use the fact that this is an exact sequence of sheaves. So for small enough open sets, you do have preimages. Because if you're exact sequence of sheaves, you're also exact at the level of stalks. Stalks are a direct limit. So for small enough neighborhoods, you're good. So one small observation that we get from this proof, if for some instance we do find a U such that this sequence is exact, oops, so is exact for all, so if there exists U for all P greater than 0, then not only we get that this long exact sequence in Czech homology, but we also get the long exact sequences in the Czech homology with respect to that particular open thing. And now it is just the same lemma, because this is the cohomology of this cohomological complex. We'll conclude today maybe a bit early with another definition. So we take a vector bundle over M and let E be its sheaf of sections. Then we define what is called cohomology with values in E as simply the Czech homology of this sheaf. With values. We will further explore what this means, in particular when E is a line bundle. And yeah, the idea is that, you know, if here you put C, you're just thinking of the cohomology of functions, so basically differential forms. While here, yeah, you're thinking basically differential forms, but with values in the bundle. Instead of values in the trivial bundle, you have values in the bundle. Okay. So yeah, even if it's a bit early, I think this is enough material for today. And Czech homology is a bit full of indexes, let's say. and of direct limits. So we're really mixing quite a few things together. So is there any question?
I don't think so. Maybe just one thing on the first how do you say it, on the first slide. I think we yeah, I was just wondering why you said an element is a family of sections, but that's just due to the does that have something to do with the last thing that we just said? Like
Yeah, I mean, I don't, maybe I didn't introduce it before. Sorry about that. But like an element of f u alpha, sometimes
yeah.
I will call it a section of f over u alpha, even if, I mean, this is in principle just an element of some abstract abelian group.
Okay,
Right?
but the motivation derives from this.
Yes and yes and no.
Okay.
I'm thinking it more. So if you remember, whenever you have a pre-sheaf,
Yeah.
you can associate a sheaf to it. And if you start with a sheaf and you do that construction, you get the sheaf back. Right? So if you have a pre-sheaf, you associate a pre-sheaf.
Yeah.
Of course, a sheaf is a pre-sheaf, so we can build that same thing. And if you remember how we built it, we take like f stalkwise, and then we do something with it. But still, so if you take a sheaf and you apply that process, you can still see f as the disjoint union of its stalks with some topology.
Okay.
Right? So I can still think of this like as a section in the sense that you send every point to an element of its stalk. So that's also why I'm thinking of it as sections. Right?
Yeah. And that is the same you said yes and no to my question whether that's motivated by our last definition, but that is the association in the end, right?
Yeah, I would say so. I mean, every time because you still think of this as a projection, no? To every, you take f, you have your f, which okay, is not a bundle, it's a functor. So, but if we think f as this collection of stalks,
yeah,
then you just think that you take an element, this is part of a stalk, and I project it to x. So very much in a bundle-like fashion.
Yeah.
So that's why I want to talk about sections. So yeah, I think it does probably come. This name does come from the fact that it resembles the section of a bundle.
Yeah.
And in particular, when we do have a bundle, it's sections for a sheaf. So kind of makes and this is kind of the reason why we do this, no?
Yes. No, just I try to have a visualization of it, but yeah. Okay. Good. Apart from that, I don't have any particular question. So yeah.
Okay, so I will let you munch of this on this for today.
Yes.
And tomorrow we will see more theorems regarding this Czech homology.